It's okay. Yeah, just let me get where I need to be here. Okay. Uh, I'm going to show you a Core 1 actually blinking an LED. How about that? On a $30 board. That's hello world for us hardware people. And let me show you the absolutely complicated code. It's on your screen. So we created an opcode. I created an opcode for turning the LED on, a different opcode for turning it off. Now, the -6, what that says, when there's a minus in front of a number, that is a CFA. That's not a number. That's not a -6. We're trying to do the, and we'll change this later on to add bits to the database so that we don't have to do it this way, but we're just getting our code working. So we're just using minus numbers, and that tells the interpreter that no, that's not a number. Don't put it on the stack. Jump to that boot ROM place. So -6 says jump over here. So 6 is literal. So we're going to put 65,000 on the stack, or 650,000 on the stack. Another literal, we're going to subtract it. So we minus this an opcode. We're going to duplicate that. We're going to test it to see if it's equal to 0. And if it is, for you hard ass fourth builders, you know that O branch means that branch only if it's 0, and branch means always branch, right? So branch is like again, and then O branch is like, until, except for it's only 0, right? Testing for 0. So this is the extremely complicated code to make that LED blink on a $30 board. Now here's what's kind of interesting. So I've been kind of shooting from the hip a little bit as to what the performance of the Core 1 would be. This particular board is only running at 12 megahertz. It has a 12 megahertz clock. It could go higher than that, but that's what it is. So we can extrapolate this to a 200 megahertz part, but next meeting, I will try it on my new board, my new $10,000 board here, which is my space board. That's the FPJ. And amazingly, I was able to JTAG that on my first board spin. I was sweating bullets. Yeah, with this one, I can actually see what the Core 1 is doing because we'll be running it like 250 megahertz clock. And it has 481,000 LUTs. This little board here that we're running on only has 5,900 LUTs, and we're not using that much of it. So let's take a look at a couple things. So I did some calculations, and Brad or you other guys may, tell me I did it wrong, and that's be typical. But so I counted the steps in the code, and it's basically 17 instructions. And it does this 1.3 million times. So 12 times 1.3 million is 15.6 million operations per second. So let me know if I did that wrong. What's interesting, though, it's only a 12 megahertz clock. The reason you can get faster than the actual clock rate is because what was Bob was talking about was we use what's called blocking statements. So I want to go through some of this code. Now this code here, let me take this and uncomment it. And while we're we're looking at some other code. I'll show you printing to a terminal. That also works. I'm not just blinking an LED. I can actually print to a terminal. How about that? Let's see. Let me get this synthesizing. Because right now, all this code resides inside the FPGA. There's no external ROM. There's no external RAM. The whole thing runs in a $5 FPGA using only FPGA internal ROM and RAM. And we all know that Forth hardly uses any resources at all. So let me get that started. A comment about the Forth computer. So originally, Dimitri made the Forth computer in System Verilog, and I'm a Verilog programmer. And I'm like shaking my head on this thing. It's like it's only Dimitri could write this sucker. So this is the Forth outer interpreter. It's all commented out, but you can see it's very complicated, and it's not Forth style. Now, this outer interpreter compiler combination code would run so frickin' fast. Well, it runs so fast that it actually does it searches the dictionary between characters and on the fly. So what we're doing is we're pulling this out. Like you can see that this is a state machine. So there's like 7 states, parses a state, compiles a state. So what we're doing is we're recoding this into opcodes, and we're going to write the outer interpreter and compiler in the boot ROM. It's going to slow it down a little bit. You know, I mean, if it slows it down to 30% of its speed, it doesn't matter. I mean, it's operating at 20 million operations per second. So what if it's 6, you know? But what's more important is the Forth way, which is factor your code and keep it simple, stupid. So that's commented out. So let's take a look at opcodes. The way that you make an opcode is the first thing you do is you have to create an enum. So here we did a type def, and we created all these different opcodes. For communications, you see that we have key and emit. So you have to create these first because our machine is using the enums, right? And everyone should know that the word equals a number. Like the very first one would be 0, execute would be 0, abort would be 1. You can actually, in System Verilog, you can do something like this. You can say equals 12, and then do that for all these other ones like you can in C. And then you could make a target compiler if you wanted to, because you know then you can compile to literal numbers that represent opcodes like any other processor. So the first thing you do is you create an enum here. Let's just take a look at so LED on. So I'm using LED on, right? So let's go take a look at the LED on. That's where I'm using it. Okay, so this is LED on. Really complicated code. There it is right there. So all we do is we put a 1 out on the port. The way these things work is, so this is the DP is the data stack pointer. Originally we, up here, you see that Dimitri on his demo, see, actually I should have this commented out because I don't have anything on the stack. I'm just assigning it. what you see up here, he's taken data stack position 0 and sending that, updating a register, which is called NLEDG. And then the second position is the blue, and the third position is the green. So this would be commented out the way that I'm doing it. I changed it to just, I just want to turn an LED on and off. But so if you notice, there's these equal signs. These equal signs are called blocking statements in System Verilog. The equal signs are like the way that Chuck Moore did green arrays. Equal sign means that this line will execute, and then this one, and then this one, but none of it is clocked. So that means that the synthesizer will use a combination of gates and the lookup table to create this functionality. So this could actually, because it's creating, think in terms of building a computer using 7400 ICs. Remember those guys? And we have people in 2020 that are building 74 and minimalist computer that are building, CPUs out of 7400 logic and prompts. So that's the way FPGAs work. So when you use the equal sign, it can actually run faster than the clock. We are clocking our computer at 12 megahertz, but remember, we got a throughput of 15, and this is why. So there's another type, this one here. Now, Dimitri should have used a blocking statement. Sometimes you can intermix them. It depends. But when you see the less than equal sign in System Verilog, that's called a continuous assignment statement. So that means at the edge of a clock period, all these variables are updated simultaneously. Now, just think if you had A equals B, A equals B, C equals A. So if you did this using blocking statements like this, you would get the correct answer, for that second, what did I call it, C? You would get the correct answer for C, which would be, the second parameter. But if you use continuous assignment, they all are updated at the same time. So now you have the wrong answer. You don't have the answer that you think of. So if you're programming in System Verilog, what I suggest you do is use the equal sign, use blocking statements, only use the continuous assignment statements for updating I/O. You want all your I/O to update at the same time. And they will teach you the reverse in school. They'll tell you make everything synchronous. You don't have to. Yeah, so here's a definition of key. Okay. Now, in previous talks, I talked about this busy flag. And what's nice about this is if key takes, and key will take longer than one cycle to execute, it might take 12 because it's waiting for the UART, right? So we have this busy flag in the interpreter. The interpreter says, I'm not going to go forward and execute another opcode until this one finishes, until the busy flag turns to false. So it will stop executing on key, and key will grab a character, and once it's finished, it will set the busy flag to false. This is why I say complex over RISC engine. CISC over RISC engine. The RISC engine is the fourth machine. Basically, what we built is an RTX 2000 and NC 4000, all shaboom, all of Chuck's computers. Now, processors are processor chip, right? They don't have any memory. You still have to add memory. With an FPGA, you can have everything. And you literally could take this. There were some people that were building an NC 4000 simulator. You could take a Core 1 and you could make any processor you want. You could, you could make an 1802, but just code up the opcodes. If you like 1802 and you want to play with it, you could do that because you control the opcodes of this computer. You can have as many or as few as you want, and they can be as complicated as you want. So here's an opcode that Dimitri's working on right now. So it's called parse. Now, parse does a lot of work. I'm not going to go into the opcode because I literally don't understand it all. But I know this piece right here, because we're 32 bits, we're storing things as 32 bits in the dictionary, but we have to parse out 8 bits. So that's what this particular piece is doing. So, I don't see people playing around with parse, for example, but parse is a great opcode. You might want to create your own outer interpreter words. Like one of the things I want to do, I want to support index notation. I don't think it's that hard. So, you need to factor out the outer interpreter into opcodes, and that's what we're doing. So now here's the 4th inner interpreter. Okay, so if reset, it does this. I'm not going to go into all this stuff because I'd have to ask Dimitri anyway. But there's some things that has to happen timing-wise. That's why he's got this skip opcode. But there won't be a test later, and you don't really need to know it. But you notice that this always statement has a pause edge clock. Okay, when you see an always statement, and with System Verilog, they added always statement FF, which means that it's clocked logic. It's flip-flop logic. If you say COMB, it means it's logic like green rays. It's combinational logic. So it's like if it says COMB, then it means that it's going to be using the lookup table on the gate. If it's got an FF, it means it's going to be putting a register at the back end of whatever it's doing. So it becomes a synchronous thing. Always statements are parallel processes. So whenever you see an always statement, that is a parallel process right there. It runs in parallel to everything else. So here's a UART. UART has its own always statement. So the UART is running in parallel with everything else. This is the RX part of the UART. And guess what? The TX part is running in parallel to everything else. They're separate. That means that you would never, in an FPGA-based computer, you would never miss a bit because, interrupts stepped on each other, as an example, on a normal sequential CPU. Everything's in parallel when you see this always statement. So here I am creating SPI control, and you notice it's on its own always statement. So this whole computer is about 1,000 lines of code, and it's only 1,000 lines because I've added a bunch of stuff like SPI, things like that. I'm adding those things for controlling a robot. It's probably like 500 or 600 lines of System Verilog code, this whole computer. All right, so we finished synthesizing. So let's go to we got 2 instances open. Don't do that. please. Okay, let's download the code. Oh, so here's the, so now it's outputting core 1. And it's also outputting an OK. It's not formatted very well, but anyway. So we are able, emit works. There's something wrong with key. I'm going to be talking to Dimitri on Monday. He's got a day off. I got a day off. We're going to be working on core 1 all day. So basically, over the next week or so, we have emit, we have key, we have the basic fourth engine working on this $30 board. And I put the links in the comments for the board, for the tools, and the GitHub. While we were in our meeting, I uploaded this code that's I'm working with here. You have to do a couple of things. The active strategy page, I think it is. Anyway, you have to update some of the stuff. Oh, here. So RAM style needs to be block RAM, ROM style, EBR. When you create the project, after you create the project, and you choose system Verilog, as when you first create the project, it asks you the language you want. So make sure that you click on system Verilog. And what I'll do is, on our next meeting, I'll go through the whole setup and how to get running. By that time, we should have a lot more of the counter interpreter completed. I'll have key fixed. So you could do things like you could, grab a key, like the A key executes one of your opcodes, as an example. B executes a different opcode. So in for 2020, there's a big discussion about microcoding. And that's exactly what we're doing here. This is microcoding. So now this is the terminal test. So we have to say literal, right? Because fourth has to know that it's a number. And it means fourth is going to put it on the stack. So I define CR up above. There's you have parameters up here. So I like to parameterize things. So CR is 13, right? And line feed is 12. So you parameterize things that make it easier to read and understand. Don't use magic numbers if you can get away with it. Make a parameter. So first thing it does, it emits a carriage return. And then it tells the inner interpreter that the next thing is going to be a C. So a system Verilog code, if you put quotes around it, it knows it's an ASCII number, and system Verilog will convert it to the C ASCII number. And then you just do an emit. How hard is that? So we do a core 1, and then we do, I also parameterize space. So you don't put the, 32 down there. And so this is showing how to use emit in the terminal. It is set for 9600 baud, 8 bits, no parity. I like real term, been using it for 30 years or something. I could put a download link to that, but you can use any terminal program. You may find that some terminal programs, you might have to do a line feed carriage return. Some of them just accept a carriage return to get a new line. So you might have to do that if you, and I defined LF also for line feed. Let's see. Yeah, so this is some of Dimitri's magic. We have a memory manager to manage the dictionary and memory. So is there any questions?
Is the memory still DDR?
What's that?
Is the memory still DDR? The one DDR3 or DDR4? Is it just?
No, there's zero memory,
Oh, okay.
external memory. The memory is inside the FPGA and it's SRAM. The memory inside the FPGA actually works at the speed of Fabric. So the internal SRAM can actually go up to 250 megahertz internally. It has like 2 nanosecond, I think, access time. It's as fast as FPGA Fabric. And FPGA Fabric also has single cycle multipliers all over it. You know, it has many of them. So single cycle multiply, you have single cycle shift. Now, we will be putting division in here, and I'm thinking using the what do they call it? Add and shift version of division. Brad, help me out here.
Mm-hmm.
You know all the different ways of implementing division.
Sorry, which one are you doing?
I think it's add or subtract and a shift, and
Yeah.
For every bit wide, it takes one more cycle.
So it's what you're doing it with a sort of a barrel shifter and a decrement, or sorry, and a subtract.
Is that the most efficient way to do it in hardware, or can you think of
I mean, it's uses less silicon. There are faster ways if you're willing to blow more gates.
So I did with one line of code. Let's see, you guys are still looking at my screen, right?
Although for divides, people particularly it tends to not be a good trade-off. Like usually you don't want to people will typically do like an inverse or things like that if you've got like most of the cases where you divide, you can afford to be slower, or you can afford to or you would rather be approximate for like graphics or whatever. So people often will not do the more expensive divider.
So I did create a divide opcode, and I let the tools create create the fabric, and it took up 500 LUTs.
Yeah.
But this board that I showed you is 481,000 LUTs. I mean, what is 500 LUTs when you have 500,000? You can get FPGAs in the 20K LUT range for about $20 to $25. And so what's 500 LUTs in a 25,000 LUT FPGA, right? So we'll be running some tests on it. We'll compare the tools and see, how fast the divide is, how many clock cycles. At some point here, it's lower on the priority list. But it was,
yeah, I would say that one usually people tend to like. Some of the ARM variants even they like leave out the divide because it's like, well, you can make do sort of. The multiply you tend to want, but but it depends, right? Like x86 blows, I'm sure does the fastest one you can do, and probably even larger ARM.
Yeah, one of my talks I gave, I did some research into modern day processors, and we hear about this 2 gigabit, processor, right? It's complete bullshit. Do you know the clock in your laptop is about 330 megahertz? I kid you not. The hardware clock, and then they're doing all this stuff. They're adding 3 layers of caches, and they got cache hits and cache misses. The reason is that you piss poor, slow DDR RAM. DDR RAM on a good day, if you get a cache hit, might be 20 nanoseconds. It could maybe 5 DDR5 might be faster than that. But if you get a page miss, it's like 125 nanoseconds. You know, it's really slow stuff. The SRAM inside this FPGA is 250 megahertz. You know, what is that? 4 nanoseconds? You know, access inside the FPGA. And you can get, you know, external SRAM that they use for caches, you know, on your motherboard. They use them for hardware caches that are between 4 and 10 nanoseconds. And fourth hardly needs any memory. So you can utilize these things. A fourth machine on an FPGA is going to be so fast. Now, I'm going to say one more thing about this, this board. So we're testing it with a 12 megahertz clock. I don't know, I'm not going to extrapolate and say that because we're running at 15 million operations per second on a 12 megahertz clock, that's going to extrapolate up to 250 megahertz. We're going to have to, you know, we have to do some real testing, but I'll do it on my board, on this guy, and I'll give you some real numbers. This is one of the most powerful FPGAs out there. It's the top of line for microchip. It's called the PolarFire RT. And so at that point, Brad, you want to turn the video off?
Sure, I can turn off the video.
The recorder.